Hi, we're so excited to be here today talking to you about soundscapes and how we can use that to explore the ocean through mapping it. So I'm going to start out by talking about something that you might not hear too often at the Esri headquarters here in Redlands. When I first started working with GIS a couple years ago, I had absolutely no idea what I signed up for or what I was getting myself into professionally. So I was looking into graduate schools, trying to kind of advance my career in a certain way, and the word GIS was thrown at me a couple different times in different contexts. And, I did what any good scientist does when you hear a new word. I looked it up on Wikipedia, kind of skimmed through the first paragraph, saw the word maps, thought that sounded fun, and so I went with it. Applied to school, got in, and it wasn't until a couple years later, after that, I was sitting in the audience of an early career event, and it really hit me that there was a deficiency in the room. And that deficiency seemed to be that there were all these really great scientists, really great people from academia doing really good science, but they were just doing that. They were publishing these papers, kind of this academic currency we have going on, but what was really happening with it after they published that paper? And that's when I realized, sitting there that day, that GIS was kind of the answer to everything that was missing in that room. It was the bridge that kind of, led the way between doing science and people actually being able to visually understand it, take it one step further, and use it. So today, we're here to talk to you from a company called Applied Ocean Sciences. I'm going to hand it over to Chris for a little bit, and he's going to talk to you about what's going on in the back end of these acoustic models, and then we're going to wrap it back into GIS at the end.
Great, thank you very much, Sarah. So by way of introduction, I'm Chris Linden. We work together at Applied Ocean Sciences, and the thing that we have in common and the reason that we work together so well is that we have both, through very different paths, realized that GIS is sort of the answer for what we're trying to accomplish. My own background is I was a military officer for 14 or 15 years, and also a PhD oceanographer and physicist from Scripps Institution of Oceanography. And I was participating in the academic currency, like you said, publishing papers in cutting-edge science. And then as a Coast Guard operator, I wasn't using any of that technology in my day-to-day job. So when I got out of the Coast Guard, I decided my mission in life would be to see if I could narrow that gap between the cutting edge of science and technology and what's available to people who are using it to do good things. And that's really the mission of Applied Ocean Sciences. So what we're going to focus on is ocean acoustics. I want to start with the bottom line up front, just in case I forget to say it later. What we've done is develop a set of tools that will allow anybody on the Esri platform to do high-end ocean acoustic and physical oceanographic modeling, data assimilation, and analysis. The reason for doing that is Sarah and I feel as though we can run our acoustic simulations all we want, but if the people who are using it to do environmental impact assessments for marine mammals or detection statistics for detecting illegal fishing in closed areas don't have access to it, then what's the point? In the way that we can get that cutting-edge science to a larger pool of people, the way we can lower the barrier of entry to doing those high-end analytics is through Esri platforms. And so what we've done is create a set of tools in Esri. By way of introduction, just very briefly, let's talk a little bit about the basics of ocean acoustics. This is my whole life, so I'm the only one in the room who's interested in it. But ocean acoustics is just the study of how sound propagates through seawater. The reason that we care so much is sound is how we see the ocean. RF, radiation, optics, light, all of those things don't travel very far underwater. So if you want to sense the ocean, measure the temperature and salinity, find a whale, find a ship, something like that, you use acoustics to do it. If you're trying to operate an ROV, you use acoustics to communicate with that ROV. But the way that sound propagates through seawater isn't just in a straight line. It reflects off the surface and off the bottom, and it refracts based on the temperature, salinity, and pressure of the water. So on that image there, you can see a source on the right and a receiver on the left, and the path that the sound takes between source and receiver is a function of the properties of the ocean, particularly the sound speed. And you need to account for that if you're going to measure the way that sound propagates through the water. And that's why it's not an easy problem. If you can do it, however, you can answer all types of very cool questions. One of the reasons that we use sound to sense the ocean is that it propagates great distances very quickly, fairly unattenuated, in ways that are predictable and a function of many of the things that we are trying to measure. So you can use the global propagation of sound around the ocean in order to measure things that are important for climate change, like the global temperature and salinity and things like that. But you can only do that if you're able to understand how the acoustic energy propagates. So this is just a really quick vertical slice through the water. So up is up, down is down, and it's sort of a vertical slice through the water of what we call transmission loss, which is a measure of how sound gets weaker between source and receiver. And then you can see scrolling across the bottom, well, the bottom of the ocean. And direct your attention there right now, you can see the right part of the screen is going to get very black. That means there's no sound there. And then as soon as the source crosses over that seamount, again, the energy's there. But it's not just in straight lines. It's sort of nuanced. And you really need to understand the entire environment in order to figure out how sound propagates. So the fundamentals of what we've done is we've taken those acoustic models and brought them into Esri. If you want to know how sound propagates through water, you start with the bottom. You add in the ocean, the temperature and salinity. You figure out where your source is in your receiver. Then you compute all of the possible paths that the sound can take between source and receiver. You integrate over all of those paths, and then you'll see a little vertical slice, just like the one we just saw, of transmission loss. And then you do that simulation in all directions, and you can see that rotating around. Then if you want to know how loud a source will be on the hydrophone in the location of that little yellow dot, you can take a slice through that volumetric data set and look at it from a plan view and use it to do things like determine how far away you could detect a whale on a hydrophone. But those graphics are awful, and they take ages to write in MATLAB or Python or something like that, and they're not accessible to the user. And a video like that doesn't really help you answer questions, and it doesn't allow you to bring the results of the simulation into a larger GIS workflow. So what we've done is take those acoustics and bring them into Esri. And to give an example of why that's important, if you're the Bureau of Ocean Energy Management today, and you're charged with doing an environmental impact assessment for a new pile driving operation, for some offshore construction, the math that you're going to do, and the math that you're regulated to do by NOAA, is that far left image. It's 20 times log base 10 the range. And so if you're trying to determine how many whales might be impacted by your construction, you'll do that very simple radial simulation. Goes equally over land, over water, bathymetry, temperature, salinity, none of those things are accounted for, which means it's a very incomplete picture of the scenario, and you might not be right. If you're the Navy or the Department of Homeland Security, you might use a different approach for your acoustic modeling. They take a couple of radials. 18 is sort of the Navy standard, and they just interpolate through those radial simulations, those vertical slices, just like we already saw, and that would be the simulation there in the middle. This is Port Townsend, Washington, by the way, an area that is very applicable to orcas and marine mammals. What we do is we are very proud of the several years of our lives we spent writing very efficient acoustic propagation models so that we can do a full 3D simulation. It runs in near real time with a click of a mouse. It does thousands and thousands of radials, and it even takes into account the horizontal refraction, bending around islands and things like that. And we get the image there on the right, which agrees with observed data far more closely. And then we've taken all of that and put it into an Esri interface. Sarah?
All right, so let's talk about why we should care about this and how you can use this as part of your workflow within your own organization. So we talked about Port Townsend in the examples above. Let's continue there. What we're looking at right now is a map of 3 critical zones, and these zones have been designated as critical protected areas because there's a lot of whales there, in particular the southern resident killer whale. It's a very endangered species. Only about 76 are left in the population in this region. So we can add data from layers from the Living Atlas, or your own layer, perhaps, and using a simple overlay analysis, see why these areas are critical. There's a lot of vessels going through here. You can see the density map where the shipping lanes are, and a lot of the boats in this image here are trying to stay out of those critical zones, which is great. But if we add another component to this analysis, the acoustical footprint, we can really see just how significant that impact is. Even if the boats don't go inside the critical zone, it doesn't mean that their impact is restricted to just the outside. So not only are we able to do this over a single point in time, but we can take real-time data, AIS data like we heard about earlier today, and actually step into the tail of a whale and put ourselves in that place to see what they are seeing in the ocean. And if you're a whale, you're really receptive to acoustics. That's how you communicate, that's how you're gonna find a mate, how you're gonna find food, and it really gives us a new perspective and makes people care by visually seeing what is going on in that region. So let's broaden the scale a little bit and move out from that sound we've been talking about. Here you can see kind of a wider perspective, and you really can tell through these sound fields how it's being driven by the local environment. If we look at the sound fields that are a little bit closer to the sound up there, a little bit more in the coastal regions, you can see that they're contained. The sound fields are very kind of close within each other. But let's move out into the bottom corner here on the left, where you can see the deeper regions. The sound fields and the convergent zones, based on the rays and the different propagation factors going on, are really driven by that depth. It takes a long way to travel down to the bottom, and it bounces off in different ways, creating a wider scope for that. So it is really important to be able to tell not only that you're doing this acoustic simulation, but where are you doing it? Because it's always going to make a difference. So we talked about kind of the man-made noises, and that's one part, but what about what's going on naturally before humans cause that impact? Wind gives us a really good idea of the general soundscape, kind of a baseline. No one was around before boats were moving around the ocean, so you don't really have that true baseline. But we can, create a makeshift baseline, in a sense, by connecting to these other data sources. So we have our man-made sources, we have our natural sources. Now let's combine them. By combining them, we're able to get the total ambient noise all across the ocean, and we can do this using these efficient models at a global scale. And this is really cool. This is really important because we're entering this age of technology where there's so much data available. We're able to use cloud computing, we can use these real-time satellite feeds, and we can really get a sense, using the geophysical kind of environment going on, how this is going to look and what impacts it's going to cause. So, creating modeling, creating predictive layers is all fantastic, but let's take it one step further and see some other questions that we can ask. So we've been talking a lot about kind of global and what sounds can be produced from sources. What if you wanted to hear what is possible to be heard at a certain location or not heard? This is the Ocean Networks Canada. It's in the same region we've been talking about today. And it's a series of hydrophones. It's an acoustical array connected through cabled observatories. And if we were to zoom in on one of these hydrophones, we'd be able to take, there it is. We'd be able to take these acoustic simulations, build them on top of each other, accounting for the depth and different pressure sensitivities that are at those different depths, and be able to calculate what you could hear from that particular source and what you could do about it. So let's say that you had a hydrophone there, a boat's driving over the top. You're gonna wanna know, using that hydrophone, because its purpose is to listen for things, can you hear it or can you not? So you can kind of break down and go in the opposite direction we've been going now. This is the acoustic transmission loss, sound propagation, coming off the single hydrophone. Using this, we're able to calculate, using the sonar equation, what the ambient noise is and what's going on at that particular point in time. Use raster algebra to create detection zones, meaning that on a quiet day, you're able to hear different factors and different sort of interactive things. Maybe it's a whale, maybe it's a boat driving over the top, depending on how loud everything else is. Just like if I didn't have this microphone on, it might be a little bit harder to hear in the back of the room versus if you're sitting in the front row here. It's a little bit easier. It just depends on everything else that's going on in that particular moment in time and how you can kind of hone down on what you're looking for.
So that last figure, by the way, is the detection areas for a 165 decibel, which is not uncommon for a fishing vessel, as a function of the Beaufort scale. So that's something that you might be familiar with. It's basically wind levels. 1 is flat, calm, and 12 is 65 knots plus, and it's a hurricane. And so the yellow area there shows you the area that you would be able to detect a 165 decibel fishing vessel at the surface on a very loud day, and the blue, or the entire region essentially, is the area that you'd be able to detect that same vessel on a very calm and very quiet day. And so that's just sort of one of the many, many questions you might be able to ask if you're trying to monitor illegal fishing or something like that. But really the takeaway isn't the specific pieces of analysis that we did. What we really wanted you to walk away with is that with us bringing these acoustic simulations through Esri and making them available to anyone, you can start incorporating the acoustics into your own GIS workflows in ways that we probably haven't even thought of. Everything from conservation activities, bioacoustics, surveying, environmental monitoring, and a lot of other applications, because sound is how we see the ocean, and now we can see that sound. So as Jack likes to say, we can see what others can't. So thank you very much for your time, and I think we have a few minutes for questions.